So today we are moving on to 1.3, which is solving equations with variables on both sides. So going over, we just have one vocabulary word for today. It's identity. It's something that's always true, something that doesn't change. So your identity is something that you are born with. You can't change that. Same thing in math. An identity is something that is always true. 1 + 1 is always going to be equal to 2. That's an example of an identity. So moving on to solving equations. There are several steps that we are going to be using to solve our equations. Depending on the equations, you're going to skip some of these steps. So let's see. Step 1, we're going to use the distributive property. So anytime you've got parentheses, you want to get rid of those first. The next thing you're going to do is simplify the expression on each side of the equation. In other words, you're going to look to see if there are any like terms that you can combine. So are there any constants that can be added together? Are there any variables? So you have an x plus another x. Can you add those together? So looking for any like terms you can combine. Step 3, you're going to collect the variable terms on one side of the equation and the constant terms on the other side. In other words, you're going to get all the variables on one side of the equation and get everything that doesn't have a variable on it, move it to the other side of the equation. Then we're going to go to getting our variable by itself, isolate the variable. So remember our steps, we always get rid of addition or subtraction first, then multiplication or division second. And then we always want to go back and make sure we are checking our answers. Okay, so special solutions. So equations may not always just have one solution. An equation that's true for all values is called an identity. And the way we're going to answer that is we're going to say it has infinitely many solutions. An equation that is not true for any value is going to be no solution. So these are going to be two of our special cases that we're going to come across. We're used to getting x = 5 or y = -7. Today we could come across ones where there are infinitely many solutions, meaning every single number you could plug in for x would work, or no solution, meaning there's not a single number you could plug in for x that would come out to give you a true answer. Okay. So I want you to go ahead and try number 1, see what you can come up with. If you get stuck, come back, or when you get finished, come back and see how you do on it. So as you can see, we have variables on both sides of the equation. We want to get it so we only have variables on one side of the equation. Okay, so to do that, we want to move all of our variables over. We can either add the 6x over or we can add the 3x over. I'm going to choose to add the 3x over to the other side. And the reason I'm going to choose that, though, is because I want to get it on the other side away from my constant. So when I do 12 minus 3x plus 3x, those cancel each other out. I'm left with 12 equals. And on the other side, if I do -6x plus 3x, we can think -6 plus 3, that's a -3x. Okay. Now we're down to our one-step equation, ones we've been solving since our first section. So we have a -3x is equal to 12. -3 is attached to x by multiplication. So the way we get rid of multiplication is using division, using our inverse operation. So we're going to divide both sides by -3. And 12 divided by -3 gives us -4. Again, we can think about checking our answer. When we're checking our answer, this time we actually have to plug it in for all of our x's. So we're going to have 12 minus 3 instead of x times our -4, and then equals -6 times -4. So we'll do our multiplication on this side first. So if I have a -3 times a -4, it's a +12. So I'll have 12 plus 12 on this side. On the other side, -6 times a -4, that's a +24. And 12 plus 12 is, in fact, equal to 24. So this checks out. Okay. Moving on to number 2. Again, we've got variables on both sides of the equation, so we want to move all of our variables over to one side. So I'm going to start by adding a 5z over. When I do that, I move all of my z's over to the right-hand side. That should be a 17 plus 10z. Okay, all my variables are on one side, so now I just need to get my variable by itself. So I'll start by getting rid of that 17. So if I subtract a 17 from both sides, 7 minus 17 is -10, and it's still equal to my 10z. 10z, they're attached together by multiplication. Anytime I have a number next to a letter with nothing in between them, it's multiplication. So to get rid of multiplication, we're going to use division. So I'll divide both sides, and I get z is -1. Some of you may be sitting there thinking, well, could I have done it in the other direction? So if we look at our original problem, could I have moved my z's to the other side instead? So let's check it. If I subtract this 5z over to the other side, let's see what happens. So this time my z's cancel out on this side, and I'm left with 7 minus 10z. Be careful with that math. -5z minus 5z is -10z, and it's still equal to 17. I still need to get my variable by itself, so I'll subtract the 7 from both sides. I have -10z is equal to +10, and when I divide by -10 on both sides, I get z is equal to -1, which is the exact same thing we got using the other way. So my point of doing it two different ways is to show you that it doesn't really matter which side you move your variables to. As long as you're using your rules correctly, you can move it to either direction and then get the variable by itself. Okay. Number 3. So this time I actually have some like terms that I need to combine on the left-hand side of my equation. So I've got a 6x minus 10x that I can do. So I have 8, and then 6x minus 10x is a -4x. So I'll have 8 minus 4x is equal to 16 minus 8x. So if I have any like terms, I want to combine those first. Once they're combined, then it's like number 1 and 2 that we already did. So I want to get all of my variables to one side. I'm going to choose to add the 8x over to the other side, but you could have added the 4x over to the right-hand side. So I'm left with 8 plus 4x is equal to 16. All right, so now I need to get x by itself. Remember, we get rid of what's farthest away from the x first, so we want to get rid of adding that 8 by subtracting an 8. So I'm left with 4x is equal to 8. And then lastly, 4 is attached to x by multiplication. So if I use division, I can divide both sides by 4, and I get x is equal to 2. Don't forget to go back and always check that answer. Make sure it does, in fact, work out. All right, number 4. This one we have to start by using the distributive property. Okay, and we actually have the distributive property on both sides that we're going to have to be using. The distributive property says that we need to take what's outside the parentheses and multiply it by everything in the parentheses. We can't do 48 minus 16x. If we could start with that for our first step, but we can't. Those are not like terms. So I need to multiply the 3/4 times both the 48 and times their 16x. Okay, so 3/4 times 48, 3/4 of 48 is... and I hit a wrong button on my calculator. Times 48. 36 minus, and now we're going to do our 3/4 times our 16, which would give us a 12, and we still have our x on it. Okay. Remember, for like terms, we're talking about addition and subtraction. So if I'm thinking about adding these two, I can't do it. They're not like terms. This one's just a constant, no x, and this one has an x. However, with multiplication, you can multiply if they're not like terms. So I can multiply my 3/4 times my -16x. Okay, on the other side, 4 times 4 will give me 16 plus, and then 4 times 2x will give me 8x. All right, now I'm back to problems we've seen like this already. So I'm going to get all my variables on one side. I'm going to choose this time to add the 12x over. You'll notice a trend. I typically like to move it to the side so that I have a positive variable, but that's just personal preference. It really does not make any difference at all. So 8x plus 12x would give me 20x. All right, so now I need to decide, do I get rid of the 16 or do I get rid of the 20? We always get rid of what's being added or subtracted first, so I'm going to subtract the 16 over on both sides, and I have 20 is equal to 20x. And then lastly, get rid of that multiplication or division, so I'm going to divide both sides by 20, and I get x is equal to 1. Again, always a good idea to take that answer, plug it back in. So if I were to plug in a 1 here and here, making sure that it does, in fact, check out. Okay, so now we're getting to our problems that may or may not have just a single solution. So we approach the problems the same way. Whether we know it's going to have a solution or not, we still start it the same way. So we're going to start by using the distributive property. So 6 times 4s is 24s. 6 times 12, let's see, that would be 72. 8 times 3s is 24s. And 8 times 14 would give me 112. So I have minus 112. All right, I've got variables on both sides, so that's the next thing I want to do. So I'm going to subtract my 24s over. When I do that, it actually cancels out here and here, though. And I'm just left with 72 equals to negative 112. So if all of your variables cancel out, and you're left with something like this, 72 equals negative 112. This is a false statement. 72 is never equal to negative 112. It doesn't matter what number you plug in for x up here. It means you are never going to have a solution. And you can try it. Pick a couple numbers. Plug it in for your s up here. Plug it in for your s here and here. And as long as you plug the same number in for each of your s's, you've done something mathematically correct. And you're going to find that you do not get a solution. It will never actually work. It won't check out. If you were to check an answer, any answer, positive number, negative number, zero, decimal, fractions, it doesn't make any difference. None of them will ever check out. Okay? All right, so let's take a look at number 6 then. So again, we're going to start by using the distributive property on this side. My left-hand side of the equation is not going to change. 8 times 2f is 16f, and 8 times 3 is 24. All right, think to yourself, what's my next step? Got f's on both sides, so I'm going to subtract that 16f over. And once again, all of my f's are gone. My variables completely canceled out, and I'm left with a number equals a number. However, this time 24 is in fact equal to 24. That's a true statement. If it's a true statement, then that's going to be what we call infinitely many solutions. Okay, it will always work, which means it doesn't matter what number I pick. If I plug it in for my f's, it will give me a true statement. So go ahead and try that. Pick any number, it doesn't matter. So for example, if I plug in 0, if I plug in a 0 here and here, let's see what happens. Well, 16 times 0 is 0, so I'm left with just 24 on this side. If I am multiplying 2 times 0 on this side, I will get 0 plus 3 is 3, and 3 times 8 is 24. So I get 24 equals 24. That, in fact, is a true statement, which reinforces that it doesn't matter. Any number I pick, I can plug in, and it will give me a true statement. Okay? So that concludes the lesson for today. Make sure and take a second and write your summary so that you are ready to go. Go back through the notes, any of them that you didn't quite understand, that you have questions on, star them so that tomorrow in class you'll have that opportunity to ask for help on those ones that you are still having difficulty with.